Consider the generic reaction of reactant A forming product B. We can consider the rate of this reaction in its differential form, where rate is equal to -1 over the coefficient in front of reactant A multiplied by dA by dt, which is the rate at which the concentration of A is changing. We can also look at the rate in another form, which we could determine experimentally, for example, using the method of initial rates. So here, for example, we could say that rate is equal to K, the rate constant, multiplied by the concentration of A to the power of n. That exponent n would be determined using the experiment. These two rates are equal to each other, so we could equate these two terms and then integrate to get the integrated rate law. The integrated rate law describes how the concentration of A changes over time, such that we could calculate the current concentration of A at any time t after we started our reaction. Here, we've set those two different ways of looking at the rate as equal to each other. What we can do now is separate the derivative and put all of the concentration terms on the left and all of the time terms on the right. We've taken the coefficient, little a, and the negative sign and moved them over to the right, and we've kept the rate constant k on the right, so that on the right side we have -a times k times dt, and on the left we have only the concentration terms, 1 over the concentration of A to the power of n multiplied by dA. We can then take the left side, which depends only on concentration, and integrate it from the concentration at time 0 to the concentration at time t. On the right side, which depends only on the time, we can integrate from time 0 up to time t. Now let's take this general approach and apply it to zeroth, first, and second order reactions. First, let's look at zeroth order. For a zeroth order process, our exponent n is equal to 0. And here, we're going to take our coefficient, little a, to be 1. So our rate then is -dA by dt, which is equal to k multiplied by the concentration of A to the power of 0. We could also just write that as that it's equal to k, since the concentration of A to the power of 0 is just 1. We've isolated our terms and we've gotten to the integral at the bottom, so let's take this integral in the bottom right and evaluate it. If we take that integral, which is on the left side, essentially just the integral of dA, since 1 over the concentration of A to the power of 0 is just 1, then that integral is just the concentration of A. On the right, our integral of -k dt is just -kt. We can evaluate each of those sides on the left from the concentration of A at time 0 up to the concentration of A at time t, which gives us concentration of A at time t minus concentration of A at time 0. And on the right side, we evaluate from 0 to t, which gives us -kt minus -k times 0. We can rearrange this equation into what will be its linear form. Here we have the concentration of A at time t is equal to -k times t plus the concentration of A at time 0. If we plot the concentrations of A at time t as our y values, and the time t as our x values, we will get a linear plot where the slope m is equal to -k, so the negative rate constant for our reaction, and the y-intercept is equal to the concentration of A at time 0. We can take the same approach for a first order process. In a first order process, our exponent n is equal to 1. So I've filled in a 1 in red in each of the steps from our original generic approach. I've kept the exponent, little a, as 1 here. Let's then take this integral in the bottom right and evaluate it. If we take this integral of 1 over a dA on the left, it would be the natural logarithm of the concentration of A. The integral on the right of -k dt is the same as before. It's just -k times t. If we evaluate the integral on the left, we have the natural logarithm of the concentration of A at time t minus the natural logarithm of the concentration of A at time 0. On the right, we have -kt minus -k at time 0. We can rearrange this again into its linear form, where the natural logarithm of concentration of A at time t is equal to -kt plus the natural logarithm of the concentration of A at time 0. If we were to plot the natural logarithm of our concentrations of A at any time t as our y values and our time t as our x values, we would again get a linear plot, this time where the slope m is equal to the negative rate constant k, and our y-intercept b is the natural logarithm of the concentration of A at time 0, our initial concentration of A. We can do the same thing once again for second order. We're going to do this second order process in two different ways. First, we're going to take that the exponent n is equal to 2 as it is for any second order process, and we're going to say that the rate is now equal to negative 1 over 2 times dA by dt because we now in our generic reaction have 2A going to B. So our coefficient is 2. I filled in each of those 2's, the coefficient and the exponent, into each step of our generic approach. We can now evaluate that integral in the bottom right. So we take that integral and we've separated out onto the left side, we have our concentration terms, on the right side we have our time terms, and we will integrate. The integral of 1 over a squared dA is just negative 1 over a. On the right, we have that 2 term that's come in, so now our integral, instead of just being negative kt, is negative 2 times kt. We can evaluate from concentration of A at time 0 to concentration of A at time t on the left, and on the right from time 0 to time t to get this expression here, which again we can rearrange into the linear form, which is 1 over A concentration of A at time t is equal to 2 times k1 times t plus 1 over the concentration of A at time 0. If we plot our y values as 1 over the concentration of A at time t and our x values as time t, we will get a linear plot where the slope m is equal to 2 times our rate constant and the y-intercept b is equal to 1 over the initial concentration of A. To get here, we had set our rate as equal to negative 1/2 dA by dt. Or equivalently, rate is equal to dB by dt. So it was focusing on the production of products over time. Sometimes this rate is looked at differently, where the rate is instead set as negative dA by dt. So instead of a focus on concentration of product forming over time, we're looking at the loss of the concentration of reactant over time. And we've left out that 1/2 term out in front. If we define our rate differently like this, our rate constant is going to be different as well. And so I filled in here a different rate constant K2 compared to the K1 that we were using in the initial approach for second order. We can then evaluate this integral in the bottom right in the exact same approach we did before, but you'll see that instead of K1, I've written K2, and that factor of 2 from the 1/2 is missing since we defined our rate differently here. The result is that in the linear form, we have that our slope m is equal to K2, whereas in the previous approach, our slope m was equal to 2 times K1. Let's compare these two approaches we've taken for second order. On the left, we took the rate to be equal to dB by dt, so the change in concentration of product over time, which is equal to negative 1/2 of dA by dt. We also said the rate was equal to K1 times the concentration of A squared. On the right, we instead took our rate to be negative dA by dt, so focused on the loss of reactants over time, and then our rate constant is defined differently, so this rate is equal to K2 times the concentration of A squared. On the left, where we took our rate to be negative 1/2 dA by dt, that 2 carries through, and in the linear form of the integrated rate law, we see that our slope m is equal to 2 times K1. Whereas on the right, where we didn't have that half term, our slope m is just equal to our rate constant K2. Our reaction itself does not know which convention we used to evaluate it, and so the 2K1 on the left must be equal to K2 on the right. You may be wondering how you can know when you should apply each of these approaches. In your question, if you were told that the rate is equal to negative 1/2 dA by dt, or equivalently that rate was equal to dB by dt, then you should use the left-hand convention. If in the problem you were told that rate has been set as negative dA by dt, then you should use the right-hand convention. If you weren't told how the rate is being defined in a particular question, then you are free to define the rate yourself, and then to be consistent within which convention you choose to use.